Hello, my students. Welcome to Saxon Advanced Mathematics Lesson 64, in which I will entertain you with a lesson that is calculation light, but idea rich. I'm going to blow your mind a little bit with some new ideas and some new notation, but the actual calculations that we do are going to be super easy. All right. In the past, I don't know, however many lessons it's been, 12 or 20 lessons, we have kind of rewritten the rules on how to graph things. So I'm going to make a chart that helps you make sense of what the heck I've been doing to your world, right? Graphing used to be so simple, right? We just drew the Cartesian coordinate system and we had X's and Y's. Nothing more than that, right? But it's gotten a little out of control. I'll be the first to admit it. Now, we've been talking about a thing called vectors. They're really just points. But we've talked about them in two different ways. We talked about rectangular form. And what we decided was that that wasn't really all that confusing. We had, oh, just a second. I want this to be 2 square root of 3. Right? We'd throw radicals in there sometimes, but we would have a right value and an up value, plus or minus. We could do it either way. Some textbook authors, John makes the point, some don't use the R and the U. They use an I and a J system, which I personally don't really like. But it would be the very same idea, except they would use an I. And because I is already an imaginary letter, which is why I don't like to use I, they would put a weird little caret over it. And I think he does this in the homework fairly often. In either case, we know that this first number represents what we used to call the x-axis back in the good old days. And this one is the y-axis. And we can graph those pretty readily, right? Again, I don't like this system at all. I think it's needlessly confusing because we already use the I for imaginary numbers, and we don't need to cause drama by using the same letter for different purposes. So boo hiss, this I like just fine. Okay, and then we decided, oh look, there's something called the polar form of this. No, it is not when this form goes jumping into a body of water that's freezing cold in January. It's a completely different way of looking at a point. And we write it like this, where this is a distance and this measures the degrees of the angle. All right, and there's all kinds of rules, right? We start at the horizon and we go around backwards. This is the hypotenuse, this is the angle, right? That's another way we've talked about it. This is completely different, but it leads to a point just as surely as this. And we've practiced going back and forth between these, and we've gotten pretty good at it, right? We got Flying Arrow in his red plane, caring for the native Inuit in their villages, and we're tracking him and helping him figure out where he'll end up at the end of the day, right? It's going well. We've done a lot with it. Now, I'm going to throw a new idea at you. And I'm going to start filling it in on this page. And then I'm going to skip and come back to it, all right? So, now we're going to talk about graphing complex numbers. What? We're going to graph complex numbers? I know, it's wickedy wild. But let's say this is our complex number. 23 plus 2i. Notice it looks a lot like this. 23, or it's not 23, it's 2 times the square root of 3 plus 2. Sorry, my mouth is not cooperating. We can graph this, and I'm going to flip a page and just quickly show you how to graph it, and then I'll come back and finish this. We can take our usual Cartesian friend, and we can call this the real numbers, and we can call this the imaginary axis. right? And we can graph points on here, just like we graph points on anything else. Let's say this is 2 times the square root of 3, and this is 2i, right? This would be 2. It's on the imaginary thing. So we would graph this point and say this is the point that represents 2 square root of 3 plus 2i, because it's 2 on the imaginary. We can do that. That's not a problem at all. So we're going to do it exactly in this format. And again, this represents the x-axis value, and this is the y-axis. And now we're calling them real and imaginary. I mean, okay, right? We can put new labels on those axes and use them to graph this. It looks a lot the same, right? So no problem there. We can put a plus here if that helps us feel like it lines up better. But the rules of how to graph a complex number in rectangular form work exactly the same. We just label the axes differently, right? Which is no big deal. The drama comes here, because we don't want to use this same symbol, but we want to have some way of showing what this point looks like in a form that's something like this. Now, different math textbook authors have different opinions about how that should look. And John gives us a stirring debate on the pros and cons of many. And then I'm going to show you what he's settled upon, because I don't want to tell you the debate, because honestly, I don't think you care. I barely care. The way that many authors write it is similar to what we do when we calculate. Running out of room. Okay, what we do is we take 4, which is the hypotenuse in our triangle here that we're talking about, and we multiply it by the cosine of 30 degrees and the sine of 30 degrees, and that we call I. I'm going to write this over again. It's too hard to see. Okay, ignore that part. So it's 4 times the cosine of 30 degrees plus I, imaginary number, times the sine of 30 degrees. That will give us I on the, what we used to call the y-axis. This will give us the same information as this. It's just a slightly different form. But this is long and cumbersome. So what John prefers, and I like too, is to use this method for writing the polar form of a complex number. This works just like this, but as soon as we see this cis business, we know, oh, we're dealing with a complex number rather than just a basic vector in real numbers. This number represents what we have been calling the distance, or the hypotenuse. This represents the direction, or the angle, just like we've done it all along. Okay, this is weird. This isn't that big of a deal, right? When I tell you that all of this is the way we're going to graph complex numbers, you're probably like, yeah, whatever. But when you see this crazy business with the cis and this big, long, drawn-out thing, remember, all we're doing is expressing this same idea as we express here, but here we're flagging it with this crazy little abbreviation. We're saying, hey, y'all, we're talking about complex numbers, just so you know. All right? So we're going to spend time with this. We're going to slowly get used to it, but that's the way it works. Okay. Complex numbers when they're written in rectangular form, can be added just the same way that we've been adding numbers in rectangular form. Like flying arrow, remember he had 2 segments to his trip one day and we wrote them both in rectangular form. Excuse me, I'm not bored, I promise. And then we simply add them together, right? Minus signs, we just toss that into the mix, it's no problem at all. Complex numbers behave the same way. We can just add them together. But when they're written in polar form, of course, they don't work as well. Now, if we want to multiply, we can multiply complex numbers. But there's a nifty little form if we want to multiply. Let me write it down. This is the new part. This is the new thing that I'm telling you. To multiply complex numbers in polar form, which is to say with the cis business in it, we do 2 things. We multiply the distances, and I'll remind you in just a second of what that is, and we add the angles. And then when we're doing this, we also reduce to 1 spin. I know that makes no sense right now, but I promise it will. Okay, this is what the rest of our lesson is going to focus on explaining to you. This is the only calculation that we've had so far. The rest is just this weird, crazy, theoretical stuff that I'm introducing you to. This is easy. And we're only going to do 2 little problems and then this lesson's over. Ready? Now, John is going to write this as if it was unleashed from hell. Well, this is 64.1. Sorry, I forgot the 6. All right, it's long. I'm going to write out this big long thing, and he says to multiply. Don't worry. And these are 2 bracketed things that are being multiplied against each other. I can't fit them all in one line. John does. Because he's John and I'm not. Okay. So we look at this and we go, good Lord, in the morning, what is this mess? What are we supposed to do with this? And we look at this and we go, oh, cosine plus I times the sine. Cosine plus I times the sine. This is the angle. This is the distance, right? Angle, distance, angle, distance, angle. We can rewrite this in the shorter form that is much easier to work with. So let's do that. This becomes 5 cis 20 degrees, and this becomes 6 cis 42 degrees. Oh, that looks so much better. Remember that the CIS stands for cosine plus I times the sine of. Cosine plus I times the sine of. We just shorthand that down. And remember that when we get it into this, it is the complex number equivalent of 5 at 20 degrees and 6 at 42 degrees. We don't use this notation, but it means the same thing. So as we're starting, it helps to kind of translate this back and go, oh yeah, I do know what these numbers actually mean. That's the hypotenuse, that's the angle. That's the hypotenuse, that's the angle. Just another way of writing it. Okay, what we're trying to do is multiply these though. And that's nothing we've ever done before. So we follow the rules that I just give you. You multiply the distances. Now, which ones are the distances? Oh yeah, if we remember here, that's the distance. So 5 times 6 equals 30. That's the distances. And then we add the angles. 20 plus 42 equals 62. That's the angles. Beautiful. Now we rewrite it and we write 30 cis 62 degrees. We check the angle to make sure that we haven't gone above 360, but we didn't, so we're good. This is our final answer. Oh, okay. Will you agree with me, please? The calculation of this is not anything difficult. We multiply and we add, right? There's just some other weird stuff going on here. One more example. Example 64.2. Again, we are asked to multiply. This time, John cuts the gibberish and gives us the short version. Okay. Now, I will tell you this. The classic student response to this kind of problem is, I know I add one and I multiply the others, but I forget which is which. How do I remember which ones to multiply and which ones to add? Well, look at this problem. Would you rather multiply these two numbers or these two numbers? I don't want to multiply these two. Those are monsters. So that quickly reminds me, oh yeah. These are the distances. Remember, this is another way we can remember how this works. You know how we do this? We can think of our polar coordinates as this way. We can rewrite that to say distance, cis, direction, right? It's the same thing. It's just a different style of code. These are the ones that we multiply, and these are the ones that we add. That helps me remember which is which. So 5 times 7 is 35, cis, and then we add these, and we get 580. I slam on the brakes because I go, dude, that is greater than 360. So that I don't want that as my answer. I want to subtract out my extra spins. So I can see that if I just take 360 out of there, I'll be okay. And so I go 35 cis, and what is it, 220. That is my answer. Okay? So what are we doing? We're multiplying complex numbers. Just a second, I want to go back. Just to try to wrap your brain around what the heck it is that we're even doing. We are multiplying complex numbers. We could multiply them in this form and we would just do the usual binomial multiplication and thing. But if we have the complex number written in this form, this is just the crazy annoying version, right? We much prefer this, right? Again, John throws this in every now and then because some textbook authors like it. I don't. I much prefer this. If the complex numbers are written in this form, we have a really super fast way to multiply them. We don't have to multiply out the binomials. We follow these two simple rules. Multiply the distances and add the angles, reduce to one spin. And here are two examples of us doing just that. We're going to build on this. We're going to talk more about complex numbers and worry about playing around with them. This will start to make a little more sense. I just encourage you to remember that. Sorry, flipping back again. This format gives us the exact same format as this, it gives us the same information as this, it's just a slightly different format, all right? Keep this close to the surface of your brain and we will survive. Yay, lesson 64 is done. That's the end of week 17, congratulations. If you're hanging on at all at this point, if this makes even a tiny bit of sense to you, celebrate. Because this is that lesson is a bit of a mind-blowing experience. And if you can just stick with me, I promise you it will settle in your brain and make a little more sense. Okay, that's all. Thank you, goodbye.